Light usually moves in straight lines, but that's not always true. Near a black hole, photons are subject to immense gravitational forces that create stunning effects.
The type of black hole you just saw is a Schwarzschild black hole, which has zero charge or angular momentum. In order to render this phenomenon, we emit photons from a camera observer and use Euler integration to first compute a local update for position as a function of velocity, and for velocity as a function of acceleration. The acceleration takes the form of a Binet equation, whose solution defines the curved trajectory of a ray of light.
At every step during the photon's path, we check for intersection with the event horizon and the accretion disk. In the case of the event horizon, all light is trapped and we terminate the ray. In the accretion disk, high-speed particles release large amounts of thermal energy. We use the blackbody model to determine the wavelength of light being released as a function of its temperature at that specific intersection point. Around the black hole, an Einstein ring is created, a form of gravitational lensing where light rays bend to produce an infinitely repeating distorted spacetime. We don't need to explicitly model this effect, however, as these are accounted for with our light path integration.
Once we cross the black hole region, we project the ray onto a hemispherical texture that represents other celestial bodies in space. We can also account for other effects, such as a redshift, where due to the velocity of particles in orbit, the wavelength of some of the light is stretched, and thus shifted towards the red part of the spectrum. All images you see in this video are rendered using C++, where we improve render quality by supersampling pixels and optimize speed by using adaptive sampling and CPU multithreading.